Hello everyone, welcome. Today I'm going to show you a SAP-1 architecture CPU that I made right here in Logisim. I'm going to simulate the whole CPU and show you how it works. First of all, this is a SAP-1 architecture CPU which has a program counter, SRAM, registers, general purpose registers, two registers right here, register A and register B, and then ALU, and then instruction register, and finally a control sequence that can automatically run fetch, decode, and execute cycle right here. Okay, so first of all, I'm gonna show you the individual components which were used to make this CPU. We have general purpose registers right here. It looks like this, and then we have ALU, and then program counter, and then 4x26 decoder, which looks like this, and then individual SRAM cell, and then a total SRAM or RAM consisting of 16 SRAM cell right here. This is the circuit of the RAM, and then instruction register, which looks like this, and then instruction decoder that we're going to use in control sequence, and then ring counter or t-state counter that we're going to use in control sequence as well, and then finally the control sequence that looks like this. We have ring counter and instruction decoder here, and then the logics come into the individual pins. So this is the total circuit. Now we're going to the main, and now I'm gonna simulate this circuit and the whole CPU and show you how it works. So first of all, let me zoom in a little bit so that you can see. Give me a second. So this is the whole CPU. Now I'm gonna simulate this. Before going into the simulation, let me explain you something. First of all, we're gonna have to put the instruction set into the RAM, because if after we put the instruction set into the RAM, we can fetch this instruction into our registers, and then we can execute this. So here is the instruction set for this CPU which I made. In the memory address 0, we're gonna have this instruction load 13, means load register A with the value from memory address 13. And then in address 1 we have LDB 14, it means load register B value from memory address 14. And then in the memory address 3 we have these instructions add. In 4 memory address 4 we have this instruction store 15, it means store the current register value to memory address 15. And then in memory address 5 we have this instruction halt, and in the value we're going to store in register A from memory address 13, this is the memory address 13 and the value is 51. You can put any numbers here, and the memory address 14, the value is 25. Like I said, you can put any numbers here. We're gonna add these two numbers, but it must be below 256 decimal numbers. So because this is a 8-bit CPU, so the maximum we can count here is 2 to the power 8, means 256. So the sum of these two values must be below 256. If we can maintain this, then this can work right here. So I'm just for this example, I'm choosing 51 and 25. Okay, so we first have to put all the address values into our RAM. So we have to manually put the values into our RAM, and then we can fetch, decode, and execute this program. So before doing anything else, we have to choose the control sequence enable pin. We have to turn it on, and then again, before doing anything, first we need to give a we have to reset our PC, means program counter, before working anything. So and we have to put the instruction set into our registers into our RAM. So before doing that, we have to turn on the debug pin, because by turning on the debug pin we can manually set the values of this RAM and of this address. So we have to turn the debug pin on, and then PC reset and give a clock pulse, and our program counter has been reset. It's a good practice before doing anything. So now we have to choose the memory address 0, so it's all 0000, and we have to choose the mar in enable pin. This is the memory address in enable pin, manual, because we're doing this manually. So we have to give a clock pulse here. So this address has been chosen. So now we have to give the value in the address 00. We have the value from the right 10111. So we have to give the value right now. So 10111. Now we have to strum write. We have to write this value into memory address 0. So we're gonna strum write this 0 and give a clock pulse. So the value has been stored in memory address 0. So now we have to do this for all the instruction sets. So choose the memory address 1, which is this, and then mar in enable pin and give a clock pulse. So this memory address has been chosen. Now we have to give the instruction set value, which is from right 0 1 1 1 0 1. Okay, so we're gonna give this value 0 1 1 0 1. We need to write this. So right, give a clock pulse, and it has been written into the memory address 1. So we have to do this for memory address memory address 0 1 2, memory address 2. So this is the memory address 2. So we have to marine enable, give a clock pulse. So this memory address 2 has been chosen, and the value of this memory address 2 is 0011 from left 0011. So 0011 from here. Okay, so now we have to write this. So right, give a clock pulse. So it has been written in memory address 2. So now we have to do this for memory address 3, which is 11. So marine enable, because we're selecting this address. Give a clock pulse. So it has been selected. So we have to give the value. The value is from left 5101. Okay, so 1 2 3 4 5 1 0 1. Okay, after doing this, we're gonna write this. Give a clock pulse. It has been written into the memory address 3. So we have to do this for memory address 4. Okay, so for memory address 4, we're gonna 0100. So we have to marine enable, give a clock pulse. So this memory address has been chosen. Now we're gonna give the value. The value is from left 4 1. Okay, from left 1 2 3 4. We have to choose the right pin and give a clock pulse. So the memory address has been stored right here. Okay, after doing that, there are two other values we need to store, which are the memory address 13 and memory address 14 values. So these are the decimal values. So we have to choose the memory address 13, which is 1011. So we're going to choose this 1011. This is the memory address 13 value. So we have to stop this pin and marine enable pin, give a clock pulse. Okay, so memory address 13 has been chosen, and the value is from the right 110011. Okay, from right 110011. Okay, it's done. So now we have to write again, give a clock pulse. So the memory address has been gone there, and the memory address 13, this fellow. Okay, so we have to choose memory address 14. So the memory address 14 is 0111 from right 0111. Okay, I have to marine enable, give a clock pulse. So memory address 14 has been chosen, and now we have to put the value, which is 10011. Okay, 100 10011. Okay, right, give a clock pulse. So we successfully input all the values into our memory. Now we can just use the control sequence to fetch, decode, and execute the program. So after doing all that, we can just turn off the debug pin. So manual pin is turned off. So now we can do automatically everything. And before doing anything, we have to do the PC reset again. Our program counter needs to go from 0. So we have to give the PC reset and give a clock pulse. So PC has been reset. Now we can just fetch, decode, and execute our program. So there are basically 5 instructions right here in register 0 to 4, and the 5 instructions are store value from register from 13 to register A, store the value from address 14 to register B, then add this to value and store in register A, which is the third instruction. The fourth instruction is put the register A value into memory address 15. and the last instruction is halt. So there are total 5 instructions, and each instruction has 6 state. It means each instruction has 6 time states. So in total, we have to give 6 into 5, 30 clock pulse to make it work. So let's do this. So we're gonna give, first of all, we're gonna give 6 clock pulse for the first instruction to work, which is load the memory 13 uh, value to register it. So we're gonna give 6 clock pulse right now. So 1, 2, 3, 4, 5, 6. So as you can see, the value from register 13 has been moved to register A. You can see that, and in our PC program counter, we can see it has been incremented to 0 to 1. So we're gonna do this for our second instruction. Again 60 states, and then then we're gonna see the register for address 14 value in register B. So 6 clocks pulse again. 1, 2, 3, 4, 5, 6. As you can see, the value has been stored in register B, address 14 value to register B, and the PC counter, program counter, again incremented 1. And then we have to do again 6 clock pulse for the third instruction to be executed. Okay, 1, 2, 3, 4, 5, 6. As you can see, now uh, the sum of these two numbers has been stored in register A, and now then in the next instruction we are gonna store this register A value into address 15. So again 6 clock pulse. 1, 2, 3, 4, 5, 6. As you can see, the program counter incremented and the register A value has been stored to the memory address 15. Now we can give 3 clock pulse to stop this program. So halt program only takes 3 digits. So 1, 2, 3. So and the as you can see, program counter also incremented. So that means the halt program actually worked. The CPU has halted the program, and we successfully simulated the total circuit in this SAP-1 architecture. Now we can just do the PC reset and give a clock pulse to set the program counter to 0, and we can start this all over again. So this is it. This is the simulation. Thank you everyone. Thank you for your time. Have a nice day.